Good morning! Our goal is to investigate the motion of a charged particle in the electric field of a parallel plate. So here we have a charged particle, and here we have a parallel plate. And let's press the launch button and see what happens. Notice that the particle is deflected towards the negative plate. That must mean it has a positive charge, as it's attracted to the negative plate and repelled by the positive plate here. So today we're going to try to investigate the factors that influence the motion of that particle. Some of the factors we'll be investigating are the charge of the particle, the initial speed of the particle, the mass of the particle. In addition, we'll be investigating how the voltage of the plates influences the deflection. So these are the factors we're looking at. So let's clear a graph here. Let's give it a charge of 0 and see what happens. Well, notice nothing happens. When the particle has a charge of 0, it's neutral. And it behaves just like Newton's first law tells us it should behave. Newton's first law says an object moving in a straight line at a constant speed will remain moving in a straight line at a constant speed unless there's a force acting on it. So when the particle is neutral, well, there's no force acting on it. So it continues moving in a straight line. So our goal today is to investigate what factors influence that force. So one of the first factors we're going to investigate is the charge. Let's give it a charge of 1 and see what happens. Notice it begins to be deflected upwards. I'm going to turn on the force vector here to show that force acting, along with the velocity vector. Now let's increase the charge. We're going to go to a charge of 1 to a charge of 2. And let's see if this influences the deflection at all. Indeed, it has. It seems to be deflecting more now. Well, if it's deflecting more, it must mean we've increased the force. Let's go from 2 to 4. 4 extra protons now. It deflects even more. We must have increased the force. Let's go from 4. I say go big or go home. Let's go to 16. And that deflection was rapid. And so force is proportional to charge. That's the first connection we've made with the simulation. Because notice as we increase the charge, the deflection increased, so that must mean we're increasing the force acting on that charged particle. But there's another factor that the force is related to, which we'll investigate right now. So let's see how voltage affects the deflection. We're going to go back to a charge of 1, and we'll start off with a small voltage of negative 1.8 volts. Negative plate here, positive plate there. Let's launch and see what happens. The deflection is slight. Turn on the force vector again and the velocity vector. Let's increase that voltage. Negative 3.6. Notice we get more deflection. Let's increase it all the way to negative 10. Notice the maximum deflection is when the voltage is greatest. What if we reverse the voltage? Let's go from negative 10 to positive 10. All that we've done is we've changed the orientation of the plates. Now it's being pulled downwards because this positive charge is being attracted to the negative here, being repelled by the positive there. So notice this part of the simulation has shown us that as we change the voltage, as we increase the voltage, the particle deflects more. Whether it's a positive voltage or a negative voltage, that's the case. So we have the relationship that force, not only is it proportional to charge, but it's also proportional to potential difference, the voltage of the plates. When each of these factors increased, when charge increased and when potential difference increased, it increased the force, which in turn increased the deflection. Now we did not explore this factor here in the simulation, distance. However, the distance is measured between the plates, and it's shown here in this diagram. And so we have the equation that force equals Q, which is the charge, multiplied by the potential difference, or the voltage, which is delta V, divided by d, the distance between the two plates. Or more commonly, this formula is given by force equals Q times E, where E represents the electric field strength. In this case, for a parallel plate, it's the voltage divided by the distance between the plates. The next factor we're going to look at is the mass of the particle. How will that influence the deflection? So here's our base case, charge of 1, mass of 2 times 10 to the negative 27, 50,000 meters per second initial speed. Now we're not going to change the charge, we're not going to change the initial speed, we're only going to change the mass. We're going to increase the mass from 2 to 4. Let's see what happens when we increase the mass. It deflects a lot less as mass has increased. Let's increase it again from 4 to 8. Even less deflection. And let's go from 8 to 16. Why not? Force is acting, but it's barely deflecting at all. And so as you can see, as we've increased the mass, the deflection decreases. Why is that? Well, according to Newton's second law, the acceleration of an object, in this case a particle, is equal to its net force divided by mass. And so this is the reason why that as we've increased the mass, the deflection decreases. As we've increased the mass, our acceleration decreases. Therefore, the particle doesn't deflect as much. As mass increases, acceleration decreases. That's a very important concept in physics in general. And so there's one final factor I want to investigate that we haven't investigated yet. The question now is, how does the initial speed of the particle influence the deflection? So here's our base case once again. This particle was launched at 50,000 meters per second. So now we're going to increase that launch speed to 150,000 meters per second. Let's see what happens. We've gone from 50,000 to 150,000. Any predictions? Let's see. Notice it barely deflects. So why is that? Well, you can think of this in many different ways. One, you could think that the particle has more momentum, so it's harder to deflect the particle with more momentum. In this situation, the force has barely any time to act on the particle, therefore it doesn't deflect all that much. The last thing I want to do is to compare the deflection of a proton versus an electron. Let's see that now. So I'm going to select here a proton. There's the mass of the proton. We'll go back to that base case speed. And let's see a proton in action. So this is a proton in action. Notice it's positive. It's attracted to the negative plate. Now we already know an electron is negative. So it should go the opposite direction, right? Let's see. It does go the opposite direction. But notice that the deflection happened very rapidly. Why is that? Well, it's because of the mass. The electron is over 1,800 times lighter than the proton. So as a result, it has a much greater acceleration and deflects very quickly. I hope you enjoyed this video today and hope you got something out of it. Have a great day. Bye-bye.